Hi, my name is Silvia Mazzoni, and I'm going to be presenting about these new near-fault adjustment factors that we've been developing at UCLA, considering both elastic and inelastic response spectra. And I ran out of space, but we're looking at it from a full PSHA level. It's not just simple deterministic scenarios. On the left, I've got the researchers at UCLA. The first one is me. We have Dr. Ezra Zengin and Magdi Barapuri, and we have the PI, Professor Bozorgnia. On the right, I've put the sponsors, but as well as participants of this research. That's the value that Caltrans brings to these projects. They get involved, they provide advice, and also for me is they provide railings as to where to say and not get too excited about the many results and being able to produce a lot of things with it. So it's been a really interesting project in working with them, which therefore, of course, means that we acknowledge them also not just for the participation, but also for the financial support. So it's always fun to work with the folks at Caltrans. And yes, you see Tom Shantz's name. He came back from retirement. He pulled a Tom Brady on us. Here's a simple outline. I could spend the whole time looking at these different figures. But I'm going to focus on these different aspects of the project. We're going to look, and this is exactly what we did in the project itself. We're going to look at what is the current practice. It's very important because we want to improve on it, and we want to make sure that we don't bring something in that derails what is currently being done. We leveraged two other projects that I've been involved with at UCLA. One where we've done a full PSHA of the state of California, considering directivity, and we have a heck of a lot of data from that, as well as doing inelastic response spectra and developing models is another project we worked on. So I will show you what we used there. Then we looked at the findings, looked at the data, and then come up with some practical recommendations which bring us back to what Caltrans can actually do in their SDC. So if we look at the SDC itself, this is the latest version that is out there from 2019, which feels forever ago as well as just feels like yesterday. That was a tricky year. They've got the relationship of considering directivity in terms of an amplification factor on your design spectra. So you can apply these to a single scenario if you want, but you can also, and you should apply them to your design spectrum, which many cases can be a probabilistic or a deterministic case. There's a dependence of this factor. It's got a cap at 1.2, which is a really good number, we found out. And then there's dependence on distance as well as a period. And so those are the parameters that we're interested in understanding. How can we improve the maximum distance? We can almost call it a threshold distance. If you're beyond this point, you don't have to consider directivity amplification, and then what is the value for this factor, and then also looking at the period range that, is 0.5 seconds really the threshold, or should we look into more? And this is really where the period lengthening of an elastic response changes that period. So that's kind of an exciting thing of being able to bring everything together. So this is a project that we've presented before. We've had many workshops, a lot of excellent data. And I've generated, the first part of the project was really understanding what came out of doing a PSHA across the entire state of California with a spacing of the grid of about 5.5 kilometers between the points. We ran about 4 directivity models, well, 3 directivity models, and then they get combined to just a weighted average of the results from these. So we did with and without directivity. And each one of these different directivity models. It's the first time that this is done. Not only that, we brought in the latest NGA models, as well as using USURF3, which consists of about 1 million scenarios, I think. So that was a big effort, and a lot of data was generated because of all these sites. It was run for about 5 or 6 different VS30s, as well as a sleuth of return periods from about 50 years to 10,000 years. So it was a big effort, a lot of data, a lot of fun at looking at these data to really understand what comes out of it. The data is fascinating because you can just use it as almost a better estimate of your site specific, not quite site specific, but not quite USGS, because it's using the latest trends just to do a PSHA at your site with directivity. But then we calculated the simplification factors. And this is an amplification factor that now you can apply to your USGS spectrum or to your site-specific design spectrum, and just to account for directivity. And a lot of practicing engineers these days, because there really isn't so much more available, that's what they're using as the results from this, to just being able to apply these simplification factors. And that's what we're doing on this project. We're looking at these simplification factors and how can we compare them to exactly what Caltrans does. And what's valuable that we also have from that is a lot of deaggregation data for the no directivity case. And so it's really starting off with the data that you would have as an engineer. We've developed a lot of maps. It's kind of neat. I wanted to kind of show you the overall view that different parts of the state have different amplification factors. And the amplification factor is key because it doesn't matter what the level of seismicity is. If you're near a critical fault and there's enough contribution to it, you will still amplify, whether you have 0.3 Gs or 1.5 Gs. There's an amplification coming in from directivity. And at each site, we have data about the deaggregation on source type, as well as the individual faults and the different contributions from moment and distance. The other project, we only did 1 billion analyses in open seas, where we looked at simple bilinear. It kills me to not be able to put a degradation point at beyond some point of collapse, but that would be an additional parameter, and maybe that would increase the scale of the analysis significantly. But there's value to that because you can look back, and if you're looking at ductility design of 4 or 2 or 3, this data is valuable for that. And so that's what we've done in that project. I did the open seas analyses, and then Dr. Barampuri took the NGA ground motion prediction equations and developed modification factors to account for directivity, for inelastic response. And so we're bringing this project and the previous data together to really do some sort of quantification of these effects. And then the hardest part is really the simplification. And that's where Caltrans came in and really played a significant contribution to the very last part of the project. I'm famous for, I have a map for that. That's my response to most data, people that know me out there. And it's really helpful to look at the data before you plot it or before you actually develop your models. So you can see that these amplification factors, these are for a specific VS30, I believe it's 760. It's for a specific return period, but you can really see the period dependence, okay? So we start from 0.5 seconds all the way to 10 seconds. They're all plotted to the same scale, and you can see the amplification factor increase with period. And so that makes sense, and the period does come into play in the Caltrans SDC criteria. Fascinating and interesting to see how you can actually weigh the different directivity models as well. So we took this data and then try to understand it, what's going on, right? So in the building code, you have to account for directivity up to, right now we've got 10 kilometers or 15 kilometers. And so typically we would think that directivity comes into play within 15 kilometers of a fault. Well, if we look at the data here, you've got a site right on the fault where the amplification factor is 1.2. And this is a pretty critical point in I think this is where the highest amplification factor is. And it's pretty straightforward. You've got one source, that's the San Andreas fault, pretty easy to do your analyses on. But if we kind of zoom out, and you can see the plot of the spectra with and without directivity, there is that slight amplification. If you then kind of zoom out a little bit, and now we've got the San Andreas fault in the middle, but you can see the color distribution that it doesn't die out at 10 kilometers from the San Andreas fault. It actually goes up to plus or minus 60 kilometers. Is that influence from the San Andreas fault itself, or is it from other faults, right? So if you look at the deaggregation for the site right here, we've got the San Andreas fault in red, but then there's also something a lot closer that contributes to the hazard. So it was really important to evaluate these data and come up with something simple and not so site-specific so that we can evaluate how we can improve the SDC, not just the data itself or complicated models. It gets even that much more interesting, and we looked at many different other sites. And so from this, in that project, we did develop a web tool, very much along the lines of the work that I'd done with the NGA West 2 portal, same type of format, simple. You put in your site lat and long, you put in your VS30, you can actually weigh the different directivity models, and you get your site-specific amplification factors, nice plots, and really helps you to understand what the data is. Caltrans could use this eventually, but we really want to have something that much simpler to then adjust what we're doing in the NGA, in the Caltrans SDC. So we needed to do some models beyond that. So of course we go to machine learning, which is another way of saying just a linear regression or a multilinear regression of this data. We binned it. As I said, we've got different bins for magnitude and distance. Question is, do you look at the modal magnitude or do you look at the mean magnitude? This is something very important. We carried out the analyses in both, but it's important to take care of keeping track of which is which. So there's a lot of work that's going to come out of the report, a lot of really interesting data on comparing mean versus modal magnitudes. And then we split it up into bins. Because what we wanted to do is, how do these models and the different bins affect how we can change these different points? So it's interesting because magnitude does not come into the SDC criteria, but if I'm just plotting and I didn't show the numbers, but if you peek, I didn't quite cut out that that's a 90-kilometer distance. Magnitude 8, where magnitude 8, which is the San Andreas Fault, controls the hazard, its impact goes beyond those 10 kilometers, okay? So the impact is very much magnitude dependent. But we want to do something simple and extensible to do what we have with Caltrans that doesn't have magnitude dependence in it. And so we looked at maybe more realistic and different magnitude ranges, maybe between 7, 7.5. For these data, we also developed the supervised machine learning model, which means I learned a lot about making up big words on this one. We've got the different bins, and we want to get these amplification factors. So I've got a slew of different parameters where we have a hinged model type of thing, where I have a maximum amplification factor, and you can see the magnitude dependence in the different colors and the period and distance dependence in these curves. And again, we have them for modal and mean magnitude and different return periods and different VS30s. So there's a lot of really interesting data that is going to come out of just this research. How do we now narrow this down into coming up with recommendations for Caltrans right now? And this is where the folks from Caltrans really contributed significantly is, all right, tell me what to do with what I have. And so based on the findings that we have found and the different very specific bins that we looked at that would be applicable to Caltrans bridges, we've actually extended. So the original plots that you saw earlier in blue, and so this is our recommendation, looking at the results just of the analyses using elastic response spectra. We're extending the influence of distance to 35 kilometers, but still keeping that factor of 1.2, which is actually a really good envelope. For different scenarios and different bins, we actually could recommend lower amplification factors. And so the 1.2 captures a good range of our data. And then as you can see, we actually shifted the period range, the transition period range, to go from 0.75 to 2 seconds. Beyond 3 seconds, things get really interesting, and so we're recommending that you evaluate that with a little bit more detail, but it doesn't cover, this range covers the critical bridges in the Caltrans inventory. So this is the study and the work that we did just based on what we had done for the CEC project. Now we brought in a study, and Madhu did a lot of the work in bringing in our inelastic response spectrum models. And so a lot of work went into that, but I'm going to show you two quick figures, and got to keep your eyes open because I'm going to flip back and forth. So this is the data that I've shown you, and these are in red. You've got the amplification factors. In blue, it shows you the mean values, just to kind of give you a visual, but you almost don't want to look at those too much. I want you to look at how, in the short period range, the blue dots, if we have here, we've got the weighted model, so this is the amplification factor that we were looking at. And if we apply our ground motion models that convert elastic response to inelastic response, what we see is that our amplification factor actually goes up in the shorter period range, right? That's that period lengthening now. And so if you kind of go back and forth, you see that we need to do something a little bit better in the shorter period range. And so that was our final recommendation, is pushing the period back to 0.5 seconds just because of that period range. And so it's fascinating because we almost kind of went back to the very beginning, and we're demonstrating that what Caltrans is doing on a simple level, which is something that can be done as an initial analysis. If you then find out you need to do something more, then you can do something a little bit more specific. But this is a really useful tool and a very useful design tool for Caltrans to apply these amplification factors. And we actually brought them down a little bit in the period range, and we brought them up from distance. And so I like this plot. I was happy with it. And then Sharon said, wait a minute, give me something more. Put this into a table for me. And so that was an interesting exercise because I actually kept on programming it the wrong order. It's really important what you do first. So on the bottom figure, and it's more than the numbers, it's just the conditional. You always go back to Excel because it's the best way to show data. This on the left is the amplification factors. So you can see it, and it's the range from, if you go from 0.5 is the starting point. So if your period is longer than 0.5, and if your distance is less than 30 kilometers, it just keeps on increasing. And then on the right is the ratio of our recommendations to the current Caltrans values. And so the changes goes up in, of course, where the distance change was made, as well as, and it goes up in one range and it goes down in another. And so this we found is very valuable to just being able to create a very simple picture about what Caltrans is doing right now, and it's actually pretty good. In summary, the project started a year ago, and we're done with this part of the recommended factors. We've brought in, it was really neat to be able to leverage data from other projects. Right now, there's two parts of it that are still moving forward, of actually being able to take these amplification factors and evaluate this for actual bridge models. So Dr. Zengin and Dr. Barampuri are working on selecting ground motions, because that's another part of a different project, with targets in the inelastic spectra, not just elastic spectra targets, as well as doing some open seas analyses of bridges. And so with that brings me to the end of my presentation. Thank you. Happy to discuss it.